So here we start section 7.5. So in the early days of the discipline, only low energy superficial beams were available. You just couldn't produce much more than that. So for superficial X-ray beams, the dose delivered to the patient was limited by skin tolerance. In other words, when you start to see the skin break down, you need to back off because that's not good for the patient. So above a certain dose, which may be suboptimal for getting the tumor, adverse skin reactions require discontinuation of radiation treatment. For megavoltage X-ray beams, the relative dose to the skin is low, and that is called skin sparing. And it's one of the major advantages of MV beams. The other advantage is going to be penetration, as MV beams can penetrate much more deeply than the lower energy beams. Skin sparing is illustrated in figure 7.4. So let's go to figure 7.4 so we can look at that. So you've got a dose versus depth for an MV photon beam, which is the red curve. See increasing depth here, and you've got the amount of dose that's being deposited. Both graphs show the same value for the maximum dose. So you can see this is the low energy beam here, so you can see the maximum dose here, and this is the high energy beam, so you can see the max dose here. The surface dose for the ME beam is relatively low. With increasing depth, the MV dose rises to a maximum and then declines. The depth of the maximum dose is called Dmax, and that's denoted in the book as D sub M. And the phenomenon of relatively low skin surface dose for MV beams is referred to as skin sparing. So this is the skin sparing region, anywhere from the beginning of the skin up to the maximum, the Dmax for the beam. So this can be surprising. For an external beam of photon radiation incident upon matter, the fluence is maximum value at the surface. Now that's the fluence, remember. That's going to be the number of particles going through a cross-sectional area. And it declines with increasing depth of penetration. So you might think that the dose to be at a maximum would be at the surface and then declines, because that's where the maximum number of particles would come in. The attenuation of the photon fluence is only half of the story. We got to remember that the absorption of the energy by indirectly ionizing photons is a two-step process, and that the electrons set in motion by the photons delivered the dose. You have to consider that second step in order to be able to conceptualize why this is going on. And here's another figure for us to look at. Photons are incident upon a rectangular block of material. So let's say you got a phantom here. You've got the electrons set in motion by photon interactions. The electrons are shown as the dots, and the ionization tracks are represented by the arrows. So the photon comes in, hits this electron, and you can see the track going. It is assumed that one electron is set into motion in each box, and that each electron has a range of 3 box lengths. So in other words, you start here and it goes 1, 2, 3, and over. Same thing for this one, goes 1, 2, 3, and over, so on and so forth, all the way down. And this ignores photon attenuation. The number of electron tracks in each box is listed at the top. So you can see here, you got a track that goes through half of this particular block. That's why they put the 1/2 up here. You can see here in this block, you've got a full track going through here and half a track from this guy. So you got 1.5. In this box, you've got 2.5. Here you've got 3 because this one stops at around the same time this one starts. But you have to still have 2 full tracks here. And so you can see as you go forward here that you've got a consistent number of tracks going through this phantom. So this is supposed to illustrate why you have the skin sparing effect. Is because you don't have as many electrons up here at the surface with the ability to deposit dose as what you do further down. And this is the dose distribution that goes along with it. So you got half a track here in box 1, 1.5 tracks in box 2, 2.5 tracks in box 3, and then you've got 3 going through here. So that's why the maximum dose deposit happens here at box number 4. Now, also note that beyond DM, we have charge particle equilibrium. In other words, you've got 1 entering and 1 leaving. You don't have that in box 1 or box 2. Well, you do have some of that in box 2 here. You've got 1 electron that enters, but it also leaves. So, but you do have 1 electron entering with 2 leaving, so you don't really have it here. It's only usually around in box 4 where you've got the same number leaving as you do entering. So we have assumed the same number of electrons is set in motion in each box if you ignore the photon attenuation. If you include that, how do you expect that figure to change? The number of electrons set in motion in successive boxes will gradually decrease. In other words, there still have a buildup region, but as you go deeper, the number of electrons set in motion will start to dwindle because you don't have as many photons available in order to cause that same reaction or that same deposit of energy within an electron to start moving. So figure 7.6 ends up looking like figure 7.4, where you have that sloping downward motion. And the value of D is approximately equal to the range of the electrons set in motion by the photons. No discernible buildup for low energy photons because DM is very small due to the small range of the electrons in motion. And that's why the blue curve here starts here high and then decreases. So nominal values of Dmax for MV photon beams are going to be listed in chapter 10. So if you think about the previous discussion, you may wonder why there's any surface dose at all. You might expect it to be 0. But you see from figure 7.4 that it's not. The discussion's been oversimplified. Surface dose results from 2 different factors: backscatter electrons and a phenomenon not considered, which is electron contamination of the photon beam. In other words, we don't really have a pure photon beam coming in. As they move through the medium, they can be scattered through large angles, and some electrons can be scattered back towards and reach the surface. That contributes to the dose at the surface. In addition, photon beams have some electrons that contaminate, that are part of the beam. They're unavoidably produced in the head of the treatment machine as photons scatter off the high-density metal components in the head. Also, some electrons will be produced by this interaction of the photons in the air between the source and the patient. And that electron contamination will also produce a dose at the surface. Generally, an attempt is made to keep this contamination to a minimum, but the introduction of beam modifiers, blocks, wedges, compensators increase the contamination. In real radiation beams, there's no strict CPE at depth because of photon attenuation. The number of electrons set in motion in each box will decline with depth and therefore will never have strict CPE as we did for the case in which there was no attenuation. The energy transferred per unit mass to electrons is the collision karma. We can ignore the small component of energy transfer that leads to Bremsstrahlung. We expect the collision karma to decline steadily with depth due to photon attenuation. And that's illustrated down here. You've got collision karma and dose. Collision karma is here, and you've got dose here. So the dose is characteristic of the collision karma upstream. So you expect the collision karma to decline steadily with depth due to photon attenuation. The energy transferred to charged particles is absorbed downstream. For this reason, beyond DM, the dose at a specific depth is characteristic of the value of the collision karma upstream. When true CPE prevails, the dose will be equal to collision karma. and that's right here, where the two are equal. So that where they're equal is should be Dmax. All right, 7.6. We can relate the absorbed dose deposited in air to exposure. So if you can link the dose deposited in air to exposure, that's going to be a critical link to getting to the relationship between the energy and the dose that's going to be deposited. We're going to assume charge particle equilibrium. The mean energy to produce an ion pair in air is almost constant for all electron energies. So the mean energy to produce an ion pair is 33.97 eV. Or if you divide by the elemental charge there, you end up with 33.97 joules per coulomb. The energy absorbed by the air is going to be Q times this ratio, where Q is the ionization charge resulting from photon interactions in mass m. If you divide both sides of the equation by mass, then what you come up with here is Q over m, which, if you remember back, is going to be X. So the dose in air, which remember is going to be the joules per kilogram, is the exposure times this relationship is going to be air karma. So you've got air karma here, and that's going to be related to the dose in air. The air karma is now used in place of the exposure. So if you express X in Rankins and dose in air in centigrade, this is the relationship you come up with. So you've got X in Rankins, this in centigrade, this is your conversion factor. So dose in a medium calculated from exposure. So we're not really interested in exposing air. That's not really our point. What we are interested in is knowing the amount of dose in a medium in tissue. But it's far easier to measure the exposure in air using a small cavity ionization chamber that's used to measure the dose in the medium. So let's suppose that we would like to calculate or measure the dose in a medium at a particular location. Let's further suppose that we carve a small cavity out in the medium, out of the medium. That is, we replace the medium at a point of interest by a very small air cavity. So let's take a look at what that might look like. So we got our medium here, and we've got a small little air cavity here. We're going to assume CPE in this air cavity. So now let's imagine that we calculate or measure the exposure in the air cavity. From the value, it's possible to calculate the dose in the medium. So we first state the result and then derive it. So the dose in the medium in units of centigrade is given by this. We got the exposure, or the Rankine to rad conversion ratio, depends on the medium and the beam energy. We've got the exposure measured in Rankines, where the medium is replaced with the air cavity, and A, which is the fractional attenuation of photons to the presence of the medium. So we've got dose in air, which is the same as our air karma, which is the same as this relationship. Dose in medium basically follows the same thing. If we take the dose in the medium divided by the dose in the air, basically we can then divide both sides by the dose in air. We know what the dose in air is. We replace it here. That dose to air value is, let me see if I can find it. Remember this? That's how that gets put in there. And let's also go back. We know that this value here, when we change or when we're dependent upon Rankins, we know it's going to be this. So we end up putting this value in. All of these values here, let's see, the A and the X are here. The transmission ratio here, I'm trying to see exactly. Okay, so let's see here. All right, so we've got the 0.876. All right, so we know here that the dose in the medium, and bear with me on this one, we know the dose in the medium is equal to all of this. We know that this ends up becoming the 0.876, and we also have this factor out here, which if I can find here. Multiply by the exposure. And then we also have the value of A here, the fractional attenuation coefficient as well. So we know that all of these factors here are going to be introduced. We also know here that the transmission ratio here ends up becoming A. So we know we've got the 8.6 here times the X. The X can end up going over here. We know that this ratio here becomes A. And all of this, this value here folds up into a value here called F sub med, or the F medium. So we've got the A and the X out here. All of this folds into this. So it's not exactly explanatory as far as how this comes about. You just kind of have to follow along, and they say, oh, this is this, this is this, this, and this, and eventually this is how that comes out. A little bit of a mess there, I'll grant. All right. This is only useful insofar as the exposure can easily be measured. The exposure is not easily measured for MV beams. Therefore, this is only for use of cobalt-60 and lower energy beams. And since you guys don't use a lot of those, that's really not going to do you a heck of a lot of good. This F sub med is called the F factor, or the Rankins to rad conversion. The value depends on the photon energy. For air, F is 0.876 and A is equal to 1. Figure 7.9 shows F sub med as a function of the photon energy from muscle, water, and bone. So you can see their function here of centigrade per rad. You can see how for the different photon energies here, you can see how this changes. Most of what we are going to be doing is going to be stretching from here to here, at least on this particular graph. And we can see what those function values end up being, depending on whether it's water, muscle, or bone. At low energies, the photoelectric effect is especially important. And if you recall that tau divided by rho has this dependency. So at 100 keV, this factor ends up being 1.8, which if you go up here and you find that value, you can kind of see that at 100 keV, which would put us, let's see, this is photon energy of MeV, so that's 1 MeV. This would be a tenth of that, so about 100 keV. So we're looking at this value, bone divided by muscle. Bone divided by muscle. Okay, so I think if we took this value divided by this value, that's where it would end up being. So for the same exposure, the dose absorbed by bone will be 80% higher than that absorbed by muscle. So any bone underlying the skin treated with superficial x-rays may receive a substantially higher dose than that of soft tissue. And it's complicated by the fact that the value of A is likely to be lower for bone because bone attenuates more than soft tissue. Higher energies for dealing with the Compton effect, the energy density of bone is somewhat smaller than that of water. So we're going to talk here a little bit about dose and free space. The dose in free space is the dose delivered to the center of a sphere of a medium, usually water or tissue, that is just large enough to have charge particle equilibrium at the center, which is what this is trying to display. So the dose in free space refers to the dose at the center of an equilibrium sized sphere of material that is isolated in free space. Sphere is surrounded only by air. It is sometimes referred to as dose in air, a misleading term, as it suggests that dose is absorbed by air, but the sphere is water or tissue. It should be no larger than the minimum diameter necessary to assure charge particle equilibrium at its center. If the sphere is any larger, it will induce extra photon attenuation. So for cobalt-60 and a medium composed of water, the sphere would be 0.5 cm in radius, just large enough to guarantee CPE at the center. For low energy photon beams, equation 7.19 can be used to calculate the dose in free space for a monoenergetic beam, where A sub EQ accounts for the absorption and scatter in the sphere. The value of A sub EQ is 0.989 for cobalt. Quantity dose in free space will be used later in connection with external beam dosimetry. So again, 7.19. Scroll back to that. Is going to end up being this particular equation. And here are all the variables and what all that means. Okay, I'm going to truncate the video here, and then we will do 9, 10, 11 in the last video for this chapter.